Dear students, welcome to my classroom. We are learning tangents and secants of to a circle. And previous class, we learned the definition of secant and tangent. The line which intersects a circle in two distinct points is called the secant line, and the line which touches the circle at a point is called the tangent to the circle, and the point where the line touches the circle, that is the common point of the tangent and the circle, is called the point of contact. And also learn that uh, the radius at the point of contact is perpendicular to the tangent. And in this class, we are going to learn the number of tangents that can be drawn from a point to a circle. Students, we know that there are three relative positions of a point with respect to a circle. That is, the point maybe lies inside the circle, or the point maybe lies on the circle, and the point maybe lies outside the circle. These are the three positions with respect to a circle. Let O be a circle, let O be a center of the circle, and P be a point lies inside the circle. If we draw any line through this point P, the line will intersect the circle into distinct points. That they are the secants to the circle. So that is, we cannot draw any tangent to the circle through the point inside it. Okay, if a point lies inside a circle, it is not possible to draw any tangent to the circle through the given point. And the second position is the point maybe lies on the circle, like this. Now P lies on the circle. Now we can draw only one tangent through the point P. That is, if a point lies on a circle, it is possible to draw only one tangent to the circle through the given point. Okay. And the third position is the P maybe lies outside the circle, like this. Now, in this case, we can draw two tangents through P, like this. So, if a point lies outside a circle, then it is possible to draw two tangents to the circle through the given point. Okay, now we can conclude that number of tangents that can be drawn to a circle through the point inside it is 0, like this. And number of tangents that can be drawn to a circle through the point on it is 1, like this. And the number of tangents that can be drawn to a circle through the point outside the circle is 2. So 0, 1, 2. These are the cases, different cases. Okay. Now, let us know how to draw the tangents from an external point to a circle. Okay. So construction of tangents to a circle from an external point. So here I am drawing tangents to the circle from an external point. To take a circle with center O, and let P be the external point to the circle. Here it is the circle, and P is the external point. Now join O and P, and then draw the perpendicular bisector to OP. I think all of you know how to draw the perpendicular bisector. Draw the arcs of equal radii from O and P on both sides of OP, and then join the intersection point of these arcs, then the line we got is the perpendicular bisector of OP. Here I am marking the intersection points as M and N. Now the line MN is the perpendicular bisector of OP. Now take the intersection point of this perpendicular bisector and OP is L, and draw a circle with L as center and LO or LP as radius. Now the intersection points of these two circles be A and B. Now by joining PA and PB, we get the tangents from P to the circle. Here PA and PB are the tangents to the circle. Okay, students. Now join OA and OB. No need to join this one, these two OA and OB, but here we are proving a result that angle OAP is equal to 90 degrees and angle OBP is equal to 90 degrees. Okay, and from this we can see that the radius at point of contact is perpendicular to the tangent. And also we can observe that in these two triangles, triangle OAP and triangle OBP, these two are right angle triangles, and OB is the common side, and OA is equal to OB as they are radii of the circle. So by RHS congruency, we can say that triangle OAP is congruent to triangle OBP. As triangle OAP is congruent to triangle OBP, then angle APO is equal to angle BPO. Okay, that is angle OPA is equal to angle OPB. That is OP bisecting the angle APB. OP is the bisector of angle APB. We have to remember this result, this point. Okay. Here the OP is the bisector of angle APB. And now let us prove a theorem. And the theorem is the lengths of tangents drawn from an external point to a circle are equal. Just we have seen that we can draw two tangents from an external point to a circle. And now we are going to show that the lengths of tangents drawn from the external point to a circle are equal. Okay. So take a circle with center O and P is a point lying outside the circle like this. Now PA and PB are the tangents drawn to the circle from the point P. So PA and PB are the tangents, and here we call PA and PB are the lengths of the tangents, where the tangent from P touching the circle at A and B, then the lengths of tangents are PA and PB. Okay, so to prove this, to prove that the lengths of tangents are equal, that is PA is equal to PB. To prove this result, we have to make a construction that join O to A, B, and P like this. So now let us prove that PA is equal to PB. So as OA and OB are radii of the circle, we have OA is equal to OB. Now, in these two triangles, triangle OAP and triangle OBP, angle OAP is equal to angle OBP is equal to 90 degrees, because angle between radii and tangents are equal to 90 degrees. And also, in these two right triangles, OAP and triangle OBP, we have OA is equal to OB, because radii, these two are radii of the same circle, so that we have OA is equal to OB. And also OP is the common side in these two triangles, isn't it? So OP is equal to OP, which is common side. So now in these two right triangles, we have one side is equal and the hypotenuse are also equal. So by RHS congruency, we have triangle OAP is congruent to triangle OPP. So from this, we can say that angle OPA is equal to angle OPB. As also, we can say that PA is equal to PB because these two are congruent parts of, corresponding parts of congruent triangles. So PA is equal to PB. So hence proved. Okay. So we also to remember this point is also because this is very important result throughout this chapter. And let's solve some problems in exercise 9.2. The first one is choose the correct answer and give justification for each. The first question in this bit is the angle between a tangent to a circle and the radius drawn at the point of contact is 60 degrees, 30 degrees, 45 degrees, and 90 degrees. These are the options. And we know that the angle between the tangent and the radius at the point of contact is 90 degrees. So we already proved this one. So the answer is 90 degrees because the tangent at any point of a circle is perpendicular to the radius through the point of contact. Okay. So take the second one. From a point Q, the length of the tangent to a circle is 24 centimeters and the distance of Q from the center is 25 centimeters. The radius of the circle is, the options is 7 centimeters, 12 centimeters, 15 centimeters, 24.5 centimeters. Here the figure is like this. This is the circle with center O, and from the external point Q, a tangent is drawn which touches the circle at P, and the distance of the length of the tangent QP is 24 centimeters, and the distance of Q from O is given 25 centimeters, and now we have to find the radius of the circle, that is OP. So here triangle OPQ is right triangle because we know that the radius at the point of contact is perpendicular to the tangent, so that triangle OPQ is a right triangle. So by Pythagoras theorem, we have OQ square is equal to OP square plus PQ square. Now by substituting the values PQ and OQ in this equation, we have OQ is 25 and PQ is 24. So from this we get OP is equal to under root 49, which is equal to 7. So OP, the radius of the circle, is 7 centimeters. So A is the right option. Now take the third one. If AP and AQ are the two tangents to a circle with center O, so that angle POQ is equal to 110 degrees, then angle PAQ is equal to, so options is 60 degrees, 70 degrees, 80 degrees, 90 degrees. And the figure is like this. So here we can observe that AP and AQ are the two tangents to the circle with center O, and angle POQ is 110 degrees. And students, we know that the angles at P and Q are 90 degrees because these two are the angles between the radii and tangents at point of contact. So angle P is equal to angle Q is equal to 90 degrees. So here OPAQ is a quadrilateral, and in this quadrilateral we have angle P plus Q, and Q is equal to 180 degrees, as these two are right angles, so that we have angle A plus angle O is also equal to 180 degrees. Okay. So from this we can say that angle A is 180 degrees minus 110 degrees, which is equal to 70 degrees. So the right option is 70 degrees. Okay. So take the fourth one. If tangents PA and PB from a point P to a circle with center O are inclined to each other at angle of 80 degrees, then angle POA is equal to 50 degrees, 60 degrees, 70 degrees, and 80 degrees are the options given. So here the figure for the given problem is like this. Tangents PA and PB are the tangents drawn from P to the circle with center O. And it is given that angle APB is equal to 80 degrees. Okay. And we have seen that OP is the bisector of angle APB. That is angle OPA is equal to angle OPB is equal to 40 degrees. So angle APO is equal to 40 degrees. And now we have to find angle POA. Angle POA. That is angle between OA and OP. So by angle sum property, we have angle POA is equal to 50 because we know that sum of angles is 180 as the first angle is right angle and the second angle is 90 degrees. Then the third angle is 40 degrees. Second angle is 40 degrees. Here we have 90, here 40. So the third angle is 50 degrees. So the right option is A. So fifth one, in the figure, xy and x dash y dash are two parallel tangents to a circle with center O, and another tangent AB with point of contact C intersecting xy at A and x dash y dash at B. Then angle AOB. So we need to find this angle here. So here the options are 80 degrees, 100 degrees, 90 degrees, and 60 degrees. So to find this answer, join O and C. Now, PQ is the diameter and AP, AC are the lengths of tangents drawn from A. So that we have AP is equal to AC. And also angle OPA equal to angle OCA is equal to 90 degrees. Also OP is equal to OC because they are the radii of the same circle. So we can say that OCAP is a square. And we know that in a square diagonals intersect the angles at vertices. So angle COA is equal to 45 degrees because we know that angle POC is equal to 90 degrees and OA bisects the angle at O. So that angle COA is equal to 45 degrees. And similarly, we can show that angle COB is equal to 45 degrees. Now, the angle AOB is the sum of the angles angle COA and angle COB. So angle AOB is angle COA plus angle COB, which is equal to 45 degrees plus 45 degrees and is equal to 90 degrees. So the right option is C, 90 degrees. Okay. So take one more problem. Two concentric circles of radii 5 cm and 3 cm are drawn. Find the length of the chord of the larger circle which touches the smaller circle. Here we have two concentric circles. Concentric circles means circles with same center. Okay. Here the larger circle is the circle with radius 5 centimeters and the smaller circle is the circle with radius 3 centimeters. Okay. Now, here we have to find the length of the chord of larger circle which touches the smaller circle. So, let O be the center of these two concentric circles of radii 5 centimeters and 3 centimeters. So, here we have the center O and this is the circle with radius 3 centimeters and this is the another circle with radius 5 centimeters. And AB is the chord of larger circle which touches the smaller circle at P, like this. Here AB is the chord of the larger circle and touching the smaller circle at the point P. Now we have to find the length of AB. Okay. So to find length, join O to P and A. And given OP is equal to 3 centimeters, OA is equal to 5 centimeters because these are the radii of the circles. And now we have angle OPA is equal to 90 degrees because the angle between the radius and the tangent at the point of contact is 90 degrees. Okay. So radius at point of contact is perpendicular to the tangent. This is the reason. And now in the right triangle OPA, by Pythagoras theorem, we have OA square is equal to OP square plus AP square. So that by substituting the values OA is equal to 5 and OP is equal to 3 in this equation, 5 square is equal to 3 square plus AP square. And from this we get AP is equal to 4. So this length AP is 4. But we know that the perpendicular drawn from the center to a chord bisects the chord. That is AP is equal to PB. So now AB is equal to twice the AP because AP is equal to PB. Now AB is equal to 2 into AP and we have 2 into 4 which is equal to 8. So the length of the chord of larger circle which touches smaller circle is 8 centimeters. Okay students, that's all for today. And in next class we are going to solve the remaining problems in this exercise. So don't miss the next class. And in next class we are going to learn how to draw the pair of tangents from an external point to a circle also. So don't miss the next class. It's very important. Until then, see you. Bye.